Hello, my name's Dr. Stuart Auld and I'm currently an Impact Fellow at the University of Stirling. Today I'm going to talk to you about some work I did with Tom Little and Phil Wilson at the University of Edinburgh that has recently been accepted for publication in Oikos. Hello Oikos readers. So I'm going to talk to you about a study we did looking at how parasite traits change over the course of a growing system in a naturally co-evolving host-parasite system. So the host is the crustacean, Daphnia magna, and the parasite is its sterilizing bacterium, Pasteurella ramosa. So what did we do? We did a combination of field study and controlled laboratory experiment. So in the field, we looked at how parasite prevalence changed over time. And like most epidemic systems, there is a peak and then there's a decline. We also looked at how the density of parasite transmission stages changed over time. So the number of transmission stages per host, parasite burden, if you will. Now this result was quite remarkable. We found that when we took infected hosts from the end of the season, they had over 10 times as many parasite transmission spores as hosts collected at the beginning of the season. Right, quite a big change. Now this dramatic increase in parasite burden was associated with a decrease in the density of infected hosts. The fewer hosts there were, the more spores per host. Now this got us thinking. So it could be that the parasite's changing over time, or it could be that the host was changing and that the parasite was infecting a different genotype of host, or that the host was of different quality, perhaps it was better fed, I don't know. So we wanted to disentangle this in the laboratory. Now the interesting thing about the Daphnia pasteurella system is that it's really experimentally amenable. You've probably read other studies using this system. Excuse me. So you can freeze the parasite and it remains infectious. And that's what we did. As we were doing our field survey, we were freezing samples of the parasite over time. You can also have tremendous control over host genotype. So Daphnia can reproduce both asexually and sexually, which, I mean, is remarkable in itself. But it also means that we can do experiments where we can expose the same parasite, so expose different parasite samples to genetically identical hosts. And that's exactly what we did. So we had beakers of genetically identical hosts, like here, where here I have, this is the same genotype replicated 4 times. We had quite a lot more replication than that, you'll be pleased to hear. But we have 4 genotypes of hosts, and we expose sample parasites from across the season to those host genotypes. We found consistent results across the host genotypes. The parasites collected at the end of the season were more infectious. They proliferated faster within the host, so for the same duration of infection, they produced dramatically more spores when collected at the end of the season, as opposed to the beginning of the season. Parasites collected at the end of the season also elicited a much stronger host immune response, here measured as the density of circulating hemocytes per host. Now, another thing that's quite remarkable about this is theory predicts that parasites that proliferate more rapidly are more virulent and cause a greater harm to the host. Now, we didn't find that. Parasites collected at the end of the season, even though they were more infectious, they proliferated more, they elicited a much stronger host immune response, they didn't kill their host any sooner. In fact, we found a hint that they may even be slightly less virulent. Now this was a non-significant trend, a p-value of 0.06, but they certainly weren't more virulent, that's for sure. So Well, I hope this teaser is exciting to you, and I hope you go on to read the paper. And I hope it inspires people to go out into the field and do more work to look at how parasites are changing in naturally co-evolving systems. Thanks for listening.